So we're going to explore here the volume of a cylinder versus a cone in the context of related rates. So what we're going to do here is we're actually going to imagine that these objects are getting bigger from the height. The height is going to expand, they're going to get taller, and we're going to come up with the formulas of how the volume would change. Of course, we're going to do here cylinder versus cone, but more generally, notice a cylinder is just a circular prism and a cone is just a circular pyramid. So what we're doing here also applies to the more general case of prisms versus pyramids. Good, so let's think here. We do want to build some intuition, build some anticipation. What do we expect that our dV/dt formulas are going to look like? Well, imagine you have a cylinder and the height is changing. It's getting taller. What else does that change? Well, it's going to change the overall volume. If we double the height, we will double the volume. Will the radius change? And the answer is no. The radius would not change if we only change the height. Now, we could do another problem where both the radius and the height are increasing, but we're just going to increase the height here. So there is no change in radius, and we do not expect that the volume will depend upon that because it's just not changing. So, of course, we have to relate everything here. So the volume of the cylinder is pi r squared h, and r is a constant here. That radius is not going to change. So our change in v, now v prime here represents the derivative of the volume with respect to time, or dV/dt, is going to be pi r squared h prime. So the only change in v is going to happen if h changes. That's it. R is constant, pi is a constant. So there you go. That would be the formula for your cylinder, but it's different with the cone. Think about the cone. If we expanded the height, if we doubled the height of this cone, it would go out, and the top of the cone would be a bigger circle with a bigger radius. So here we see some interdependency between the radius and the height. If the height changes, the radius will. There's no way around it. That is, unless I suppose you could hold the radius constant, but your cone after you doubled the height would not be proportionally the same. The whole idea is here that you maintain proportionality as your cone expands. Okay, so the volume here will be 1/3 pi r squared h, but this time r and h are both getting bigger. If h gets bigger, r will get bigger, which means r and h are both functions of time. So to take the derivative here, we have to use the product rule, which would be 2r r prime h plus r squared h prime. And so we see here there's a lot more dependency for the volume of the cone, the change in volume. It depends upon, right, again, you're doing this at a given moment in time. At this exact moment in time, how is the volume changing? That's going to depend upon the height at that moment, the radius at that moment, the change in the radius at that moment, and the change in the height at that moment. So whereas the change in the volume of a cylinder only depends upon two factors, the given radius and the change in height, the cone depends upon four: the radius, the height, and the changes in both. And this will be the case with prism versus pyramid, right? Prisms, the change in the height will not affect its other dimensions. Whereas if you're dealing with a pyramid and you want to maintain proportionality or similarity, a change in the height will affect other measurements as well. And of course, the overall volume will depend upon that.